My name is Kevin. Like was said, I'm a data scientist at Salesforce. I'm coming from California and I'm not a morning person, so that is double low energy. So I made sure to chug a coffee right before this, and now it's ramped up. So I'll be talking about a lot of the work that we've been doing at Salesforce on automating machine learning pipelines and many of the problems that we have encountered and some of the solutions that we have developed for some of these problems. So hopefully interesting, even if you haven't necessarily dealt with a ton of multi-tenant machine learning problems like we have, but let's get started. So I figure I should put at least one slide explaining what Salesforce is and does, because before I worked there, I think I knew that they existed, but didn't really have an idea of what Salesforce does. The short answer is kind of like everything. They have their hands in almost every aspect of business automation that there is. So they are behind a lot of online stores in commerce, so they're powering stores for brands that you probably have shopped at. They're powering a lot of marketing, automation, email sending, targeting, that kind of stuff. They got their start doing normal like sales rep type stuff like lead scoring, lead tracking, opportunity tracking, but they're now involved in like running case routing and customer service centers, all sorts of stuff. So the point of this slide is mainly to show that there is a wide variety of data that Salesforce collects and deals with and powers, and there are a ton of machine learning use cases that go on at Salesforce. And so I will talk about a small chunk of them, a small but growing chunk of them. And so for a lot of the machine learning practitioners in the room, you're probably familiar with maybe not these icons, but this general flow in when you're creating machine learning applications. So there's usually an ETL step at the very beginning where you have to get your data in a format where it's actually amenable to doing machine learning. It's usually not sitting at rest in the proper formats or like, you know, in whatever way you'd like to ingest it. There's usually some cleaning that you have to do. There's then the important step of feature engineering, turning the actual fields that you have into features that you can, or numbers that you can then feed to an actual machine learning algorithm. There's of course the training of that algorithm. There's usually a feedback loop where you train a bunch of models, evaluate them, pick the best one for your purpose. Maybe have that feedback into feature engineering, change some of your feature engineering steps, etc. You then have to deploy your models and actually serve scores. And then provide a mechanism for updating the model as more training data comes in, and maybe rolling back models if things fail. So there's a lot of DevOps challenges in the last two that I won't really touch on, but feel free to ask me what can go wrong there after the talk, and I have plenty of stories there. Also, I'll mostly be talking about the top-ish row, and mostly the data cleaning, feature engineering, model training type stuff. So the extra problem that we face at Salesforce is that we are developing machine learning applications for our own customers' use cases. So we're not doing this on our internal data only, we're doing this on our customers' data, which they own, they are in charge of, they customize very, very heavily. And each customer might have many different use cases that they want to use machine learning. They might have marketing use cases, they might have sales lead scoring, they might have case classification, like support ticket case classification type problems that they want to work on. So all of those come from different data sets that are that customer has, and so you end up having to do this giant process many, many times for many different customers and many different use cases. And so automation is kind of there out of necessity. In that there is literally not enough data scientists in the Bay Area to train all the models by hand, to do all the data cleaning by hand that we would need to do for this. So that's kind of the motivation for why we're doing automated machine learning in the first place. And I'll talk a bit about so the main use case I'll talk about is what's called prediction builder, which is you imagine you have a table of data or any source of data, and you basically want to predict any field from any of the other fields in your data, and you can set that up entirely in a custom way. So that's kind of like the use case, the most general use case that this stuff applies to. And so, as we all know, when you automate things, nothing ever goes wrong, there's no problems, and everything works very smoothly. So the rest of the talk will be about some of the places where this can bite you and some of the things you might want to watch out for. A lot of this is kind of specific to the data that we have, so it's not necessarily problems that you might have, but depending on the data you're dealing with, maybe you'll see similar stuff. So what are some of the problems that you can have? So I'm first going to show a very, very simplified version of what some of our problems might look like. So the source of a lot of the problems that we have is that there is a version of the cold start problem that we have to deal with, in the sense that when we first build a model for a customer, we only have a snapshot of what their data looks like at this moment. And so that snapshot can contain data from a long time, depending on how long they've been using Salesforce. They could have data that goes back years, even decades. But we only get to see, what it looks like right now. We don't actually have, every timestamp of every modification to all the records when we start out. Later we do, but not at the very beginning. And so it looks kind of like just a normal database, where you've got IDs. Let's say this is like a lead scoring type problem where you want to predict which one of these IDs all correspond to people you're trying to sell products to, and you want to predict, well, who are the people who are or who are the records that are most likely to convert? Who do I want to spend most of my time? Who do my sales reps want to spend most of their time on? Who are the good leads? Who are the less fruitful leads? And so there will be data filled out about just contact information about these. There will be tons of custom data specific to the business and specific to the domain that will be in there. We don't have, we know what the schema will look like, but we don't necessarily know what fields have been added beforehand. But we can figure out we store the data, so we know what's in there. But there will likely be lots of lots of more specific stuff than just contact info. And so I've called out 3 fields that are relevant for making these predictions. So this is a closed by, which would be an ID of whatever sales rep finished this lead. There might be a reason why this lead was lost, and there might be an amount that this lead was for. This is all just data that's sitting there in the database. And so I'm not showing what the label is here, but you can imagine that the label these records would count as positive examples. These would be examples of leads that converted, stuff that we'd want to classify as positive. Those would be examples of things that we'd want to classify as negative. But I'm not actually showing the label field. The label field might be off somewhere on the right. It might be a formula. It might be a foreign key in a different database saying that, like, hey, this is converted into an account object or an opportunity object or something like that. But all these columns here will be treated as features when we're training our blind model. And so this is basically a textbook binary classification problem. We've got 2 outcomes, like success or failure, and we just want to train, so we can train any of our favorite binary classification algorithms: logistic regression, random forest, gradient boosted trees, normal decision trees, depending. We can try all of them and see which one performs best on this data. But there are, so I've put the checks and X's there to remind you what the actual label's in. So can anyone spot some problems that we might have with using these features and trying to make these predictions? Just yell them out, or free text. Oh yeah, that's, yes. Featurizing these, huge issue. I usually talk about that a lot. I have 1 slide on this in this talk. That is a hard thing to do in general, and is one of the things that we have to automate. But that's a less of you can do it. So that's not. Let's say even if I featureize these texts, let's see a problem. So the thing that I would want to make the prediction on is this record, the record that I don't actually know the outcome for. But the machine learning algorithm, it's really just looking for, at its heart, it's just looking for patterns in relationships between the features and the label. Different ones are better at extracting different amounts, or different, more complicated relationships, I guess. But at its heart, all machine learning algorithms are doing that. So the machine learning algorithm will say, hey, I found a great predictor. I found that if the amount is filled out, you're probably going to be a positive record. That's great. Look how good I'm performing. It will also say, oh, if I have a closed by, which notice I specifically made it doesn't follow the supposed business practices of this data. It should be filled out for everything that has a label. It's not. That's a very common thing that we have, and you've probably seen in your own data exploration issues, is that the data does not always fit the rules it's supposed to, and so we have to be prepared for that. We can't make the assumption that that's always going to be there. And similarly, the machine learning algorithm will find, well, hey, when reason lost is filled out, we are much less likely to have a conversion. If it was just these 4 data points, then it would be a perfect relationship. And so any machine learning algorithm worth its salt will say that, hey, amounts and reason lost are your 2 most important features. Some machine learning algorithms will only pick up on those features. If you use something like a random forest, it will also pick up on the other features if you use enough trees and it samples correctly. But the problem with all of those is that these are things that are all filled out after I know the label. These are not actually things that I want to use as predictors. So the machine learning algorithm will say, hey, I'm doing a great job. I have 100% accuracy, 1.0 AUROC, any kind of metric that will look way too good to be true. But this is a classic label leakage problem where you have proxies for your label just hiding in your features. And if a human looked at these would kind of be hiding in plain sight. A human would not have a very hard time realizing that, hey, reason lost might not be a good thing to use as an input feature for predicting whether a record will be lost or converted or not. So the question is what to do about this. And there are, that's the problem. Your models will look way too good. And more importantly than they will look too good is when you actually apply them on records that you don't know the outcome for, they'll just often give you random predictions because they won't have actually learned the signal that you're wanting to. Or if they have learned that signal, they've spent too much time on the nearly perfect predictors that they won't have learned that signal well enough. So you won't get models that perform very well in practice. So the first step that we tried is let's just remove these features. If we don't put them in our models, then we don't have to worry about them messing up our algorithms and being important features when they're really not. So the easiest thing you can do is look for strong relationships between features and the label. You can do this before you actually train the machine learning algorithm. And so after you've vectorized things, after you've turned all your fields into features, you can compute pretty simple statistics like correlations for numeric fields, whether or not a field is null. Do any of those things nearly perfectly correlate with the label? If so, get that feature out of there. It's not something that you're going to want to use in actual prediction. Depending on the field type, you might have to use a different type of calculation. So for example, for categorical fields, something like Cramer's V is more appropriate, which is, it's basically just a metric of how strong a relationship between a chi-squared test between 2 variables is. So it's also a value between 0 and 1. You can also compare training and scoring distributions. So one of the other things we have to deal with is that the customers set up training filters and scoring filters for their data. We're not in charge of dividing it into training data and scoring data. That is something that the customer sets up. But we do know what rows correspond to training data and what rows correspond to scoring data. It's basically, is the label defined or not? There's sometimes more complicated conditions on there, but you can at least compare fields in the training set to fields in the scoring set and say, hey, is there a big difference between these fields? Today, for example, in the case here, if I were to compare the training set, which is these 4 records, the scoring set, which is this, I'll notice that the scoring set never has closed by, reason lost, or amount filled out. And I can do this with, if this is a really strong relationship, I can figure that out with pretty high accuracy. using a variety of distribution comparisons between training and scoring sets. So I'll pause here. If anyone has any questions so far? Yes.
This seems like a mechanical deterministic step.
Yes.
Is this something that you just automate?
This is something that we can automate.
But do you automate? Like, for example, since it's your client's responsibility to split into training and scoring, do you then say, hey, red light?
So it depends. So for pilot customers, there is a lot of back and forth between us and them. It depends on.
So the software doesn't just bounce it back. It would be like.
So it will fail to produce models if some of these checks fail. So it won't actually produce a model. The customer will be alerted, hey, a model failed. There'll be some error reason, and then they will they basically the admin at that company who's running their Salesforce instance will basically follow up with what that error means and how to fix it. There's documentation on all this. It typically doesn't involve a human-to-human interaction once it's past the pilot phase. But for pilots, yes, there's a lot of like getting on calls and explaining to customers like and asking them like when is this field determined? Is this field a predictor? And it can be actually hard to determine with a lot of certainty, should I be removing this field, should I not be removing this field? But yes, this is automated right now. So I mentioned I will have one slide about how we make the feature vector. This is usually, so basically we have this library on top of Spark that creates a feature transformation DAG that has a lot of different transformation steps. And the secret sauce to this is that because we're Salesforce, we know the schema of the data that the customer has. Even though they're heavily customizing it, we know that like this field is an email type, or this field is like an address type, or this field is a pick list, like a categorical type. So that means we can apply different feature engineering strategies to these they're customized to these types. That's basically as specific as we can get. For the general use case, we can also encode specific features for like standard objects. Like if there's a standard lead object, we can say, hey, here are some other features that our data scientists have come up with that we know are predictive in other cases. But in general, we'll do automated things like for emails, we can check, classify, is the email spammy, we can pivot out the top domains from it. For phone numbers, we can check if the phone number is valid. We can pull out the country code, join that with other location information. For things like numerics, we can automatically bucketize them if we want. We can, of course, keep track if they're null or not and keep track of the actual number. For freeform text, there's a lot of different things that we have to do. One of the most important is detecting the language. We're a global company and deal with clients all over the world. So, and also some of our clients are multinational companies that have multiple languages present in their own data. So knowing what language you have is very important. You might want to do different tokenization strategies. You don't want to use just one uniform text tokenizer, because some languages don't have spaces. And so, for example, we might use top TF-IDF terms for freeform text. We often do simple things like hashing text. And the zip code example, we're not actually doing that right now. That's more something we're not pulling out like what the average income or the population is, but you can do similar things with that. By knowing that information, you can pull in any kind of external data that you want for that use case. So this is all combined into a giant feature vector of numbers, and that's basically the thing that we're working with when we're trying to find correlations and trying to figure out which features to remove. Yep.
So if you're dealing with a company with multiple different languages, I don't know if you're multilingual, but have you had to do any NLP with other languages, and how do you approach that?
So there are some very simple things that you can do without really knowing anything about the language. So for example, using the right tokenizer for that
Counting
language.
terms and...
Yes.
Yeah,
So
yeah.
we have specific custom stop word lists for different languages. We have specific, not tokenizers that we've made, tokenizers that exist in the wild for different languages that we use. So that's the most basic thing. that you can do. Without knowing the content, there's not really a lot that we need to do that's
Okay.
content-based, because we're already blind as to what that field represents and what the use case is. So most of it is just making sure that we're not using like the wrong tokenizer or removing the wrong kinds of stop words, that kind of simple stuff.
Because the company that I work at, they've started to ask us to do multilingual things, and being only an English speaker, I'm like, I don't want to open that door.
Yeah, I mean, we have specifically been I mean, this is in there because we have been specifically asked by companies to have this because it's very important for them. But yes, it's not easy necessarily. So yeah, some of these feature engineering steps are basically classifiers themselves. So the language detector, that's basically a small classifier inside that runs, on a per row basis. So how do you actually remove features? So I just want to say that there are many different ways that you might want to try. If you want to measure these kind of correlations, there's a lot of different things that you might want to use. For numerics, you can use things like Pearson and Spearman correlation, which you're probably familiar with. For categoricals, if you're comparing a categorical feature to a categorical label to see how strongly they are, how strongly related they are, you can use a chi-squared test. Specifically, what we use is Kramer's V, which is basically a measure of effect size on the chi-squared test. We're less concerned with like, is this statistically different, and more, what's the magnitude of the difference? And if you have numerics and categoricals, you can use something like interclass correlation to determine, are there very strong relationships between some of the classes in the label and some of the classes in the data. Of course, the DAG that I showed you on the previous slide was a very simplified version. It had like one layer of transformations. In practice, we have many layers of transformations, and they vary depending on feature type, how many we have. And so if a feature that comes from like a transformation near the top of our DAG is removed, we have to remove all the children of that because we don't want that information to propagate into any of our other derived features. So we actually have to do some like graph traversal stuff to figure out which features downstream we remove. And being able to do this in a performant way is not just a given. We can, the answer is we can. It's a little bit expensive to do, but it is possible and it is necessary. So we do it, but it's not necessarily cheap. And so there's one more example I'll show of a very similar kind of issue where these kind of correlation tests don't work. So let's imagine that instead of having the presence or absence of a variable, it's just the size of a numeric value that's correlated with the label. So in this case, that's something like expected revenue, which is only filled in after something is converted or after the label is determined. But instead of being present or absent, it's 0 or numeric. Or it's 0 or like whatever the number would actually be. So when you vectorize it, I'm showing the relevant piece of the vector. So if you go back, the zeros are turned into zeros. These numbers are still persisted. We keep track of those. The second number is basically keeping track of whether that field was null or not, which is something that we have to do with everything, because there's often information encoded in nulls. In this case, none of them are null, so those are all 0. And we can calculate the correlation between any of these columns and the label. The label has just turned into 1s and 0s. The problem is that if I look at the correlations, the correlation for this column will be really small, because when it's 0, the label is 0, but it has to be it depends on the size. In this example, it has to be on the order of 10,000 for the label to actually be 1. So the correlation itself is very, very small. So if you try and remove this feature with a correlation check, it won't work, because you'll typically put a threshold of like, anything above 0.9 correlation or 0.95, get it out of there. In this case, your correlations will say, hey, I've got like 0.000 something very small. It's a very small correlation, so I won't remove this feature. It will stay in. How do I get rid of it? It's very obvious, again, it's very obvious to a human that this is not something I want to use as a predictor, because whenever it's bigger than 0, that means I have a success. And I don't know it until after I have my label. So what you can do in a case like this is you can basically figure out the buckets that you would want to place this variable in. You can use a single feature decision tree to basically auto-bucketize this feature and figure out, are there any splits in this variable that are relevant for predicting the label. And so you can just try that on any numeric field that you have and see, use like a really high min-info gauge to see like, is there anything that like really jumps out as being too obviously related between the feature and the label. In that case, your decision tree will likely find an easy split at 0, and we'll say anything bigger than 0, that means true. Anything 0 or less, that means false. Yes?
Why don't you just do something like a t-test there?
So you could, and I'll also talk about other ways that we can find this. So so this was historically the first way that we tried to deal with this. You could also, yes, just look at the distributions. Is that what you're asking? Yeah.
So,
You can look at the distributions.
As like
Yep.
the categories for a t-test and
Yep.
the expected revenue as the outcome, you would see that there would be a statistically significant and
Yep.
probably a large effect size for that as well.
Yep, that's also something that you can do, and and so the key is you'd have to keep track of the effect size because that's usually what you'd want to cut on. And you can also just, again, look at the difference between training and scoring data. You can see that if you just, I've got these slides right there. You can also look at the difference between training and scoring, and if you do, depending on how balanced your data is, you may or may not be able to see that there is a difference. In this case, I specifically constructed it so that there is an obvious difference, but if you're doing, so we use a variant of the KL divergence check called the Jensen-Shannon divergence, which is just normalized and symmetric. So yeah, you will likely be able to see this in the distributions also. It's not doing this is not the only way. But if you bucketize it, then it turns into a categorical, which you can one-hot encode. This one means you're in the 0 bucket. This means you're in the bigger than 0 bucket, and this means whether you're null or not. So that's what it would look like. And then you can just use any kind of categorical checks and throw it out based on that. So that's one way of doing it. You can also look at distributions to do it. There's often multiple ways to throw out these features and cleanse your data. I forget when I started. Okay, I'll skip the next thing, because that's just more of that. And I'll show one last thing that we have to worry about when actually evaluating these models, and like what it looks like when the models are too good. So normally we have training and a holdout split that we do. So we are not in control of the training and scoring split because we can't control when the label is determined. But when we have the label determined, we can split it into a training set and a holdout set, which of course we do. And you can imagine training a bunch of different models on that training set, and evaluating it on the training set, and then evaluating it on the holdout set. And you'll typically get stuff that looks like this, where your model will perform better on the training set than the holdout set. And the harder part, so there's a lot, I wanted these words to come gradually, but the harder part here is because we don't have time information in that snapshot of training data that we're training on, the real evaluation that we want to do is this time-based evaluation where we now watch the records evolve in real time, and these icons just correspond to what the label is. So in this example, my training set would be these first 3 records, A, B, and C. They're the only things I know the label of at training time. But the stuff I would want to evaluate on is I would want to evaluate on these records that don't have a label yet, but later in time do have a label. I'd also want to evaluate on records that don't even exist yet at training time, but will later have a label, months down the line. So this is the actual true test of how well the algorithm is doing in practice. And we refer to this as time-based evaluation to not get confused with normal evaluation on the training set. And the problem with this is just waiting for enough data to be available often. So often the time scale to determine the label for these companies is on the order of months. And so we don't have this data available. Ideally, once we have enough of this, we'd want to train on this data also, which we do. But it's not available for a long time after we start constructing the model. But once we have it, we can use this as on our older orgs as a way to experiment on new ways of featureizing things and doing model selection and stuff like that. But yeah, it's just a comment on how hard it can be to actually get a true evaluation measure. Yeah.
How much additional data? It seems like every time something actually gets to a resolution, you can just take it back.
Yes, yes. So that's what we want to do. We want to look at it in a future state and say, hey, do you have a label? And do I have a case? I also need a case in my data where it doesn't have a label, because I need to know what it looks like before it has a label.
So are you planning on doing this continuously, or
Mhm.
you just
Yes.
wait till the batch?
Yes. So well, we do. We usually do this in a batch format where we'll pull data every. It depends. It's on the order of like 15 minutes to hour timescales, which is usually enough for to capture all of the changes. But yes, we basically continually check, do we have enough data to do this? If we do, do this, we've got, regression tests and things that will check how well this is doing on orgs that have been around for a while. Yeah.
So how does this compare with something like, I don't know, how often do you want to retrain, for example?
So that's a great question, and we are currently working on ways to figure out when to automatically retrain. Right now, we just have a time window that we'll pick. So if the model is more than a month old, we'll retrain. That's our simple rule right now. But what we want to do is actually use this information and say, hey, when has the data changed enough, or when has the model quality dropped enough where we want to retrain? Maybe we can use that model for like 3 months. Maybe this model is bad next week. And so that's something we're definitely working on right now, because that is important to have like different model training cadences for different orgs and different use cases. But yeah, it's we don't have a done solution for that yet. But we are measuring like data drift and stuff, like how fields looked a year ago compared to how they do now. Should we be using data from a year ago? Often not. Yeah, that's complicated. Yes.
Have you, as you're doing this evaluation, have you found there to be significant degradation as a result of the actual use of the model in UI, right? Basic promise of model. Since you have the opportunity to be looking at this over time,
right.
have you found that to be the case?
We have not found a good way to test that. But that is something that I am also curious about. So not all of these scores are actually used by humans. Some of them are used in just automated business practices. They're fed into ways that the client will automatically segment their data. So they're not always looked at by a human, but they are often acted on in some way. So yeah, that's a tough thing to measure, and I don't have a good answer for that. But it is definitely something we're curious about. Okay. I think we're basically done. So I forgot when I started, but I'm pretty sure that like 9:48. I'm pretty sure my time's up. So I just want to do 2 plugs. Most of the stuff that I've talked about, we just recently open sourced the library that we use, that I work on, that my team works on. To do this, it's called Transmogrify, so you can find it on GitHub under Salesforce. If you have any contributions you'd like to give, that's built on top of Spark. If you use Spark, please feel free to contribute. And like everyone else here, we're also hiring data scientists, so feel free to talk to me afterwards. Thank you.